Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 4.50. Problem statement says, ethane is chlorinated in a continuous reactor. And then they give this reaction mechanism right here. Some of the product monochloroethane, this right here, is further chlorinated in an undesired side reaction. So this gets chlorinated further into this. Suppose your principal objective is to maximize the selectivity of monochloroethane production relative to dichloroethane production. Would you design the reactor for a high or low conversion of ethane? Explain your answer. Hint, if the reactor contents remain in the reactor long enough for most of the ethane in the feed to be consumed, what would the main product constituent probably be? What additional processing steps would almost certainly be carried out to make the process economically sound? Okay, so you would want a low feed conversion. The reason for this is as long as ethane is present, your reaction will likely want to follow this mechanism, right? As long as this is present. But if you get a high conversion and then this thing starts to get really low concentration, then this becomes preferred, right? So then you're going to start consuming some of your product. You'll start losing it. So you want a low feed conversion, so you make sure that this is always present in your reactor. So you want to keep the concentration, you also want to keep this concentration low. Because as long as this concentration is low, then you'll be able to get, you won't form much of this because there isn't a lot of it in the reactor, okay? It's less likely to be formed. Okay. You must then have a recycle stream where the reactant, ethane, is fed back to the reactor, and you must have a stripper to remove your product and the HCl. Like, if you don't want HCl building up in concentration in your reactor, because then eventually your reaction wouldn't want to drive in this direction. So you have to remove that as it's produced. Okay. Part B. Take a basis of 100 moles of monochloroethane produced. Assume that the feed contains only ethane and chlorine, and that all of the chlorine is consumed and carry out a degree of freedom analysis based on atomic species balances. Okay, so what we've got here is I've highlighted in red all of the unknowns. So we've got 3, 6, 8 unknowns, right? And then how many independent equations do we have? Well, when we have a reactor that has like actual chemical reactions going on, you can't do just pure species balances because you have consumption and generation terms, right? So you don't have independent equations based off of your components anymore. So I mean, you can still do mass balances around them, but they're not going to be independent, right? That's the key. So you can do 3 independent atomic balances because there are 3 independent elements in these reactions, okay? And the atomic elements are carbon, hydrogen, and chlorine, and all of them are participating in the reaction, and all of them change ratios and proportions depending on the molecules that they're forming. So each one of those are independent. Now, if it doesn't meet those conditions, for instance, if you had air going in and air going out, and that was just a solvent, and it wasn't really participating in the chemical reaction except to be, like a catalyst or something like that, well, then it wouldn't be an independent balance. Like the oxygen and nitrogen in the air would not be independent from each other because they're in the same ratio in the beginning and in the end. Okay? Okay, so we have 8 unknowns and 6 independent equations because we have this process specification, this process specification, and this process specification. So that's 3 process specifications. That's 3 equations, independent equations. So we're missing, we have 2 degrees of freedom, right? Okay. Part C. The reactor is designed to yield 15% conversion of ethane and a selectivity of 12 moles of monochloroethane per mole of dichloroethane with a negligible amount of chlorine in the product gas. Calculate the feed ratio and the fractional yield of monochloroethane. Okay, so this is the fractional yield and this is the feed ratio. Okay, and then they just gave us 2 more process specifications, right? 2 more process specs. So now we don't have any degrees of freedom anymore. Okay. So let's start off by writing down our atomic balances. So for carbon first, this is our first atomic balance. We say how much carbon is going in and how much carbon is going out. How much chlorine is going in, how much chlorine is going out. And this is an atomic balance, not a molecular balance. So this isn't the molecular chlorine balance. This is the atomic chlorine balance. Okay. That's why you have 2 going in. For Cl2, there are 2 atoms of chlorine, right? Okay, so that's where that comes from. Then for hydrogen, same thing. Every molecule of ethane has 6 hydrogens, so that's why you multiply it by 6. Okay. And then the same thing, this monochloroethane has 5. Dichloroethane has 4. Okay, and so on and so on. That's how you do those atomic balances. Okay, so then I'll write down some of I wrote these down. You don't actually end up needing them, but I wrote them down just in case we needed to do a mass balance or something like that, but we didn't. We just had to do our molecular balance and our atomic balances, so you don't need these. I wrote them down. You feel free to write them down, but you don't need them for this problem. Okay. So we've got our process specs that they gave to us. Okay, so I just wrote those down just so we had them in equation form. So the sum of all the mass fractions in stream 2 should sum to 1, and the sum of all the mass fractions the mole fractions in stream 1 should equal 1. That's what that means. Then I have a mass balance here. We don't need the mass balance. I was just thinking we could write that down if we ended up needing it, but we don't, so you can ignore that part. Okay, so now I'm starting to dig into, okay, I've written down all these balances, now let's start trying to substitute values in to see if we can solve them. Now these problems are actually nonlinear, the way that the variables, the way that they gave them to us, so we can't really use linear algebra to solve for all the variables as they're written. There's probably a way you could write the equations so that you could get usable information using linear algebra. You just can't get all of the stream values and the mass fraction or the mole fractions at the same time using one linear algebra equation. Okay. So you have to use substitution, basically, is what I'm saying. Okay, so that's why they gave us these easily substitutable values right here, right? So this equals this. That's kind of the thing that you're looking for when you're doing substitution. Okay. Okay. So they gave us this value, and then they gave us this equation, right? So that's just direct substitution. So we can calculate what N2 x E2 is, right? So then we substitute these values into 1, and then we calculate from 1, we calculate, and 5. They also gave us 5 as another process specification. So we're able to calculate this value, and then we're able to calculate this value from equation 1 and 5, and then use 2 and 5, okay? And then we're able to calculate this, and you just kind of step through this, okay? And then you're able to calculate this. So you just kind of go through one at a time, solving for the variable that has, each equation has a certain number of unknowns in it, but as you go through and solve, you're looking for an equation that just has one unknown, and then you're looking for an equation that just has 2 unknowns, and then 3, and then 4. As you go through, you'll have figured out the unknowns that you need along the way, and then you're able to solve it. So that's what this is. So then we get equation 7. We've figured out all of these unknowns, and so then we're able to solve for what N1 is. Okay. N1 equals this, and then you can solve for your mole fractions finally. Okay. Then N2 equals this. Here's a really important check that you can do. Look, N2 equals N1. Very important. If you look at our equations from the very beginning, you'll notice that 2 moles makes 2 moles, and 2 moles over here makes 2 moles over here. Okay, so no matter how many chemical reactions you have going on, in this instance specifically, N2 should equal N1, because you're not creating or consuming moles. Every time there's this chemical reaction, either one of these chemical reactions going on, anytime there's one of these chemical reactions going on, you end up with the same amount of moles. So the moles in this case is conserved. It's not always true. It's just in this case it is. So it's a good check to see if you did all your math right. If you didn't put like a minus sign or a plus sign in the wrong spot, you can use these two values to check to see if you did it right. Okay. We've solved for all of these at this point, and then you can solve for N2, which allows you to solve for all the rest of these. Okay. So then you just plug in the values that you solved for. This becomes the fractional yield, right? And then this is the feed ratio. Okay. Part D. Suppose the reactor is built and started up and the conversion is only 14%. Chromatographic analysis shows that there is no chlorine gas in the product, but another species with a molecular weight higher than that of dichloroethane is present. Offer a likely explanation for these results. Okay, so there's actually a third reaction going on, where all of the Cl2 is being consumed. Some of the Cl2 is being consumed in reaction 3, so it's not going toward our conversion that we want, where we want it to be turned into monochloroethane. And then this generates a heavy product, and it lowers the conversion of the ethane, because instead of having the chloride gas react with the ethane, some of the chloride gas is reacting with some of this product. Okay. All right. That is it for problem number 4.50. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.